let's review where we are in the process of learning how to use real-world observations of elasticity, price, and quantity to make quantitative predictions of the impact of a policy. We started out with the math of the definition of elasticity, and we combined it with the math of the linear demand model to come up with an expression for the B parameter of the model in terms of observable elasticity, price, and quantity. Next, we're going to use that math to do the actual quantitative prediction. Let's start with change in quantity, delta Q. Again, we have some demand curve, and by now we've actually got a numerical number for its slope. And we're trying to analyze a policy where, for example, the price is going to go up from P0 to P1. And what we want to know is how much quantity is going to decrease. Let's define delta Q. Right? Delta Q is equal to Q0 minus Q1. Right? It's just this distance. All right, well, let's actually express that in terms of the linear demand model that we're working with. Q0 is A minus B times P0, and Q1 is A minus B times P1. Now you're thinking to yourself, we don't have an estimate of A, but lucky for us, A minus A is 0. So what we're left with is a negative B P0 and a negative B P1. And if you rearrange all the negatives, what you wind up with is B times P1 minus B times P0, which is equal to B times P1 minus P0. Put another way, it is the change in price that your policy is going to cause multiplied by this B parameter, which you computed on the basis of real-world estimate of elasticity, price, and quantity. Now, what about change in consumer surplus, delta CS? I've taken the liberty of drawing out the diagram of our policy, and remember that what we're wanting to estimate is this area number 1 and this area number 2. The change in consumer surplus caused by the policy is the sum of those two areas, and the deadweight loss is simply area 2. Now, area 1 is just a rectangle, and its area is therefore simply its height times its width. The height is delta P, and the width is Q1. Now Q1 is not something we know in advance, it's something we have to predict. But in effect, we've already predicted it, because we know the change in quantity, and Q1 is simply Q0 minus the change in quantity, delta Q. So we can actually rewrite Q1 as Q0 minus delta Q, and then the area of I can be written as delta P times Q0 minus delta Q. Delta Q is something we have an expression for on the previous slide, and delta P is something we know in advance, either because it's a direct result of the policy, say for example a specific increase in the size of a tax, or it's something we've already modeled in a previous stage of our analysis. Now, we could take the extra step and actually write out all of the math of delta P and delta Q as functions of B and Q0 and P0 and P1, but that would simply confuse matters. and you already have the components of this math that you need from earlier on. Finally, area 2 is just the area of a triangle, which is 1/2 times its base, which is delta Q, times its height, which is delta P. Again, delta Q, something we have an expression for, delta P, something we already know. That's the whole story of how we use elasticities of demand to make quantitative predictions about the impacts of a policy. In the final clip, I'll say a few things about some of the challenges that arise when we try to estimate elasticities from real-world data, which will help you to think about when you can trust an estimate of elasticity, either one that you find in existing literature or one that you come up with yourself.